Okay, so monthly space news covering roughly the last month, obviously from the name. Kind of ironic here that I'm the guy talking about space news, and yet we have our guest speaker, Andrea, coming up, does this for a living and gets paid for it. So this is a little different. I won't cover all the news. We're going to leave some for her, in particular the media event that SpaceX had down in Boca Chica. She'll talk about that. She obviously is famous enough as a reporter that they allowed her to ask one of the questions. So that was the good news. The bad news was Elon Musk's response was he zoned out. Could you repeat the question? Okay, so anyway, on to the space news here. We'll start off with the status update. We've been talking about the James Webb Space Telescope quite a bit. And the good news is it really all is working. All the parts are fully deployed. Yeah, this is really interesting again. You know, it's out there. It's in the halo orbit around the Lagrange point, which is on the far side of, if you draw an axis from the sun through the Earth, you go out far enough, there's one spot where you rotate in the shadow of the Earth all the time. It's there circling around that point. It's in a 6-month orbit around the Lagrange point. And that all worked. All the parts are deployed properly. They are starting the calibration of all those mirrors. And this is a long, very lengthy process. You have 18 primary mirrors. Each one has to be individually calibrated to microscopic accuracy. So they're working on that. And that'll be going on for the next 4 or 5 months. You may see some occasional pictures coming out. I think they've had some, but they don't look like much of anything because they're mainly just doing calibration at this point. The spacecraft itself is still cooling down. When I put together these slides, which you can't see, when I put those together, that was down to minus 347, kind of an average kind of temperature. And they have to get down to 390 for most of this to work. It is an infrared telescope, so if they're going to detect heat signatures from the rest of the universe, it has to be pretty cold to be able to do that, getting down to 390. And it's on the way. Yeah, it's all radiation, so it just takes a long time. Now, they have a lot of radiators, but still, it just takes a long time. The good news was that originally they were worried, how long will the fuel last? You need fuel to maintain station. Although you're in a roughly stable orbit, it still takes some amount of fuel to maintain that orbit. There's enough left, probably the last 20 years, which is more than needless to say, everybody's pretty happy. But of course, we'll really be happy when we start to see the real images. Okay, now that was the good news. Now there was some bad news. Space weather. Remember we talked about the that solar observatory that NASA had set up last month. We talked about that. Space weather matters. Yeah, in fact, like this slide we're talking about here, space weather matters. The background of that is the aurora borealis, which is actually a symptom of what happened. What happened was SpaceX launched their normal batch now is 49 satellites. They set up a batch of 49 satellites on February 3rd. And they just started deploying them. Now they deploy them to a low orbit, about 130 miles. And they have to work their way up on their own then, using their own ion engines. They go up to 340 miles by the time they get to. That actually takes a couple of months. And they do that for a couple of reasons. The biggest reason is you don't need your big rocket that gets you up there. You can carry more stuff to that altitude. And the reason that SpaceX is also now touting pretty highly is that this is actually kind of a safety feature for orbits, that if a satellite fails, doesn't deploy properly, that's a high risk point when you first deploy. Any number of things can go wrong. If that happens, you're in a low enough orbit, there's a lot of drag, and basically it'll come down in a couple of weeks anyway. So it is kind of a nice safety feature that they have. So that's the background on this. They launched that. However, a couple of days before that, there was a big solar, well, not even a big solar, a level 2 solar flare that came out on January 30th. And so this, of course, travels at the speed of light. You could see it. So we could predict that by February 2nd, they would hit Earth. And that was known, and it was announced. But I guess they underestimated the effect it would have. So what happens is, this is basically this charged particles coming out of the sun, they hit the Earth's magnetic field, and it ends up interacting with it. And the energy from that ends up getting dumped into the atmosphere, upper atmosphere. And that's what you see. The aurora borealis is the visible indication of that. It's called the geomagnetic storm. And there's several effects of that. Because of that energy getting dumped into the upper atmosphere, it heats it up. So the higher temperature goes up. But what really mattered was that the atmospheric density goes up. That's the ideal gas law, if you will. Essentially, the atmosphere gets a little bit bigger, a little bit denser as a result of that. Turned out that increased the drag by 50%. On the aerodynamic drag, 50%. That's what they said. So it's huge. You go from just a couple of particles of air to, to maybe 4, whatever, it really slows you down. So they realized that, at that point they were saying, well, maybe we made a mistake here. But they put it in what they call the safe mode. Now, they haven't really defined the safe mode all that well, but the key part of it is that you have to fly edge on. So if the satellite is going this way, if you think about those satellites, they're normal satellites, but they have this huge solar array that sticks out as one-sided in the case of the Starlink satellites. You can think of that as a giant parachute, if you will. It's really something to slow you down. So you want to orient that thing, you're moving kind of like a knife, or think of a piece of paper slicing through the atmosphere as thin as possible. And the hope was they could just ride out the storm and then go back to normal operation. Well, it turned out, one, the storm lasted a little bit longer and the density was a little higher than expected. And that didn't do the job. Now, there's several other problems that they didn't really talk about very much, but I think these probably contributed to it. One is that when you're in that safe mode, probably you're not getting the maximum power out of your solar cells. You're focusing on slicing through the atmosphere. That might not be the ideal angle for capturing sunlight. And the other thing is that the ion engine may not be pointing in the right direction either, at least not for optimal operation. Now, they didn't go into those details, but you have to think some of that happened. The net result was they're up there in the safe mode for too long and they couldn't recover from it. So out of those 49 satellites, 40 of them are vaporized, or at least they're in the process of vaporizing the upper atmosphere right now. So they lost them. But of course, in the big picture, they're launching satellites every couple of weeks. You consider, okay, it's not that big a deal for SpaceX. But still, it's a significant amount of money that went into that. What distinguished the ones that made it from the ones that don't, I don't know. Now, it turned out this really only affected SpaceX because they're the only ones that happen to have had a launch recently down at that low of an orbit. Everything else is up higher. They're really unaffected. This is strictly an atmospheric density problem, not an electrical storm problem. You get the bigger storms, and they can knock out the electrical grid. They can fry the electronics and satellites. It's happened in the past. Actually, the early telegraph system in the 19th century was taken out by a solar flare, as it turned out. Just fried it. The province of Quebec had an outage for the whole province at one point because of solar flares. So that can happen. That's a different problem. Those are with the more intense solar flares. And you end up with electrical problems in that case. So how often do these things happen? Well, during the entire 11-year solar cycle, you get a storm like the one we had just the other day, maybe 1,700 times. So it's actually pretty often. The worst case ones are maybe only 4 times in a cycle. So those are coming. Now, the thing is, there is an 11-year solar cycle that coincides with the sunspot cycle. When you have more sunspots, that's when you're having more and more of these flares. And the peak will come in 2025. Also, if you want to go see the aurora borealis, you want to do it in 2025 for the same reason. So people are going to probably start worrying more about space movement. We've put an awful lot of satellites up lately. Luckily, the ones in low Earth orbit are usually fairly well protected by the magnetic field. The ones that are up higher, they have more of a problem. Okay, moving on. Ongoing testing. There's made kind of a big thrust for cleaning up space debris. Everybody's worrying about it more and more. And actually, the Chinese put up a satellite which did a good thing. They grabbed a satellite. This is up in geosynchronous orbit. The high one is 22,000 miles. They grabbed that satellite. It was a defunct one. It was one of their own. And they took it up to a higher orbit. Normally the ones that are up in a high orbit like that, you take them up even higher, get them out of the way. It would take way too much energy to actually lower them and get them into the atmosphere. Unlike the low Earth orbit satellites where you dump them into the atmosphere. So they did that. They came up, they grabbed it, they moved up to a higher orbit, they left it there and they came back. So that demonstrated a capability that actually they hadn't really demonstrated. It showed that they could, approach it, find the satellite, approach it, grab it, move it, and come back. Now, of course, unfortunately, that also is exactly the same capability you need for space wars. If you want to grab some enemy satellite, meaning you're not your own, you do exactly the same thing. So unfortunately, all of these space debris cleanup things, most of those, also saying you have the ability to take out enemy satellites. How they actually did the grabbing is not known. The Chinese did not provide any details on this at all. People have tried looking for clues. One clue is in the mission patch, just like we do with all of our missions. You make up a little patch you can put on your jacket, and they had one for their mission. All of their missions have ties back to Chinese folklore. In this particular one, there's a guy who would go out and fight demons and this and that, and he would always have a spear, and he had an eye in the middle of his head that he could shoot out an array. And he also, in the picture, they also had a net showing. So they might have used any of these techniques. They might have used a net. They might have used a robotic arm. They've demonstrated in space shows some robotic arms attached to satellites. We don't know. You may laugh at the idea of using a spear, but actually that's what the American equivalent satellites from Northrop Grumman do. We talked about them last year, the MEV, mission extension vehicles, where we went up to a satellite, an Intelsat satellite, that was running, and it was out of fuel, so it couldn't be used, it couldn't reliably be used anymore because it didn't have fuel. But actually the electronics worked fine, so we grabbed that. And what we do is we actually went up next to it, stuck a spear into the thruster to grab a hold of it, and then just moved it, now they're doing the station keeping, the orbit adjustments to keep them going. So any of those things are possible. Now there's a company called Astroscale. It's a Japanese company, but they're really all over the world. They are doing experiments, testing as well, of getting rid of debris, mostly at low Earth orbit. They stopped their test, which is sort of disappointing. They sent up a satellite, and they also were attached to that. They kept one that was kind of a target representing, what would be debris. And so the very first test, they just moved it off a couple centimeters, and then they grabbed it to show they could do it. That's the first step. Not much, but that's what they did. Back in August. Now, this time, they were doing they were hoping to send it off some 10, 20 meters away and do the same thing, going and catch it. They said something anomalous happened. They didn't say what, but basically the experiment is paused till they figure out what to do. So they have a long way to go. Because what they really have to do in the future is show what happens if the thing they're going for is tumbling a little bit. How do you grab it? And that's harder. And then what if you have to approach it? If it's tumbling, you have to, while it's spinning, you try to match its rotation speed, and then you try to grab onto it. Because their technology, what they do is they assume that you have cooperated ahead of time and put a magnetic disk and some pattern recognition patch on your satellite so you can easily recognize where it is and grab a hold of it. So theirs, you might say, theirs is one of the few space debris cleanup systems that really wouldn't be used as a weapon. You wouldn't put one of those magnetic devices on a satellite you were going to use for warfare. But anyway, it's disappointing that their progress is halted. You also have to wonder, why did they do nothing since last August? I mean, the first test they did was pretty simple, 2 centimeters and back. Why did it take them this long? You have to think that maybe they hadn't really worked out all the details in any case. Okay, moving on to this space Cold War that goes on. As we saw with the Chinese satellite, they're kind of demonstrating that they can do stuff that we can do, which could harm you in space. The US kind of instigated something. So the Chinese have launched a couple of satellites up in geosynchronous orbit. And one of the US 5 satellites made a point to move in very, very close to it to take pictures. And this has been going on for quite a while, but everybody's doing that. But the Chinese, in this case, showed that they saw it coming and they moved out of the way. Just the fact that they did that indicates capability that we didn't really know they had. Actually, the Russians and the Chinese the Russians and the French actually have done this for a while, along with the US. Now they've shown that they could do that too. The first time that kind of activity going on was publicly announced was back in early 2020. There were a couple of Russian satellites that were tailgating an American satellite, and we actually announced it. But it was actually going on long before that. Anyway, the way to think about it is what's going on now is it's sort of like the old Cold War, especially against the way it was against the Russians, where submarines come and they come and practically bump into each other. The Russian jets would still do buzz American ships to sort of shake them up a little bit. That's going on in space more and more now. Okay, moving on to the main topic here, talking about space-based solar power. And this was really brought up because the NSS, the National Space Society, issued a press release supporting and congratulating the Japanese for having a major project for space-based solar power. And this really was a revision of a roadmap that they'd already had. In fact, I took a look at it, and it's almost the same. I think the main difference is the Japanese are really basically committing in a more concrete way, saying they are going to be building something that will transmit power back from space in 2025 as a test from low Earth orbit. And then actually try to put a gigawatt commercial power up there by 2030. And that is new. So the milestones, they always had those, but now it appears to be a rather firm commitment. So an overview of space-based solar power. It actually goes back to science fiction, like a lot of things that are done, for instance, communication satellites were dreamed up by whatever timeline. Isaac Asimov, the science fiction writer, in a short story in 1941, just described power satellites that took in solar power and transmitted with microwaves, transmitted that to other users. They were doing it on various planets in the story. So the idea goes to there. The architecture for space-based solar power really was laid out in 1968 by someone named Peter Glaser. And there's just three components to all the space-based power. The first one is just collecting the energy. Usually that means solar cells. It could actually mean a boiler or some kind of heat engine as well, but usually solar cells. And it may involve reflectors as well, just to concentrate the sunlight. The second part is transmitting this power to Earth, which in most cases has been microwaves. Some cases also been lasers. So those are the two. And then some way to receive this power on Earth or some other location. People have talked about powering satellites or powering settlements on Mars or something the same way. So those are the three components. The key innovation really that came in with Glaser was using an antenna called a rectenna. Now this is a portmanteau word, rectenna. It's the word antenna combined with the word rectifier. A rectifier is another way of saying diode in typical devices. It's a device for converting alternating current to direct current. So if something like your household current is alternating current, if you want to convert it to direct current, you'd use a diode. Now the reason you do that is you have all these signals coming in. The radio waves are basically alternating current, but they're coming maybe at slightly different frequencies, different times. The easiest way to handle that is just to convert it all to DC and then convert it back to alternating current. So that's what they do. Now, this technology is not new. It was actually invented in '64. Everybody in this room is actually familiar with it in a way, because RFID tags, like are commonly used in inventory management. Those RFID tags, they do not have batteries. They just work by the power that's transmitted from the transponder that's looking for them. And then using that power, they transmit something back. You also are familiar with it from your easy tags. If you have an easy tag in your car, you're going down the tollway and it knows where you are. There's no battery in that little sticker that you're putting on your windshield. That's also using what's effectively a rectenna. It's really just a way to get a little bit of power out of the air. By the way, for people that are familiar with the East Coast, they have a different system called Easy Pass, and theirs uses the battery. It's a different technology. Now the difference though, when I talk about a rectenna for solar power, we're talking about something where the units are miles, or you have square miles of territory filled up, with them. Now I have a picture of what that would look like. You basically just have these huge fields, again, think square miles, and the whole thing is basically a whole bunch of little antennas are about the size of your hand, maybe 5 centimeters. So a dipole antenna, meaning half the total length of that is half the wavelength of the microwaves you're trying to receive. And there's just millions of those, and they're kind of all aggregated together. It's just a huge metal mesh on the ground, really. And that's what you're using to get the power. Now, it's been reconsidered several times in history. Typically what's happened was they look at it, they decide it's too expensive, and they kind of give up for a while. And then they go back and do a retrospective. NASA looked at this actually back in the 60s, and then they kind of gave up. They had a fresh look in '97, and then they gave up, and so on. So this goes on in cycles, and we're starting an up cycle on this again. But there's a reason for that. And the biggest thing is the launch costs are coming down drastically. I mean, Falcon 9 alone probably brought down the cost by a factor of 10. Starship will do another factor of 10, maybe 100 in the best case, mainly depending on how often you launch to spread out the fixed cost. So there's the promise anyway of costs getting a lot cheaper, because cost is the main problem with space-based solar power right now. The second thing is, of course, that the solar panels, they're getting better, the weight's coming down and so on. And also, to the extent that you have to have construction of large structures in outer space, robotics is getting better as well. So there's every reason to think that the cost of doing that should come down. The other thing is the designs have gotten better. They're much more modular now. Now they're focusing mostly on plates. You can think like the squares, maybe the size of dinner plates, or maybe a little bigger, mass-produced, and then essentially being kind of independent. So on one side, they'll have the solar cells to pick up the power. On the other side, they'll have the microwave transmission, and then the stuff in between is the electronics to accomplish that. Basically, converting the light to DC, powering the electronics, generating the microwaves, and so on. So they call it a sandwich in a lot of these architectures. This is kind of nice because if they're independent, that means you don't need to wire them all together. You save a lot of weight just in a copper wire. If we're talking, you're talking about a square kilometer or two of antenna up in space. There's a lot of wire to wire together. You don't need to if each one just transmits independently. The second thing is that you might not even need a huge structure to tie them all together. There's been a lot of different designs for that, but some of them posit essentially just have them all kind of orient themselves as they need to without even necessarily being attached to anything, or at least minimizing that. Now, if you do that, that also gets the cost way down. Think of it as a school of fish. Just have a whole bunch of fish all facing the same way, picking up your solar beam on one side and transmitting power out the other. So there are some advantages that are always cited for space-based solar power. The first thing is that, they say the sun never sets in space, and that's sort of true. If you're in a high orbit, you're far enough away from Earth, you're never in the Earth's shadow, or at least, maybe only a few times a year would you be in the Earth's shadow at all. So that means the sun is available 24 hours. That's quite different than solar cells on the land where you're limited daytime. Maybe you get 7 or 8 hours of useful sunlight on average. The second advantage is there's no atmospheric interference in getting the original power to the solar cells. So they say you're getting at least 30% more sun. And there's a lot of disputes over the exact numbers, but clearly the sun is better in space than it is going to be down here where you have the atmosphere. Right? And of course, it's cited as being clean, no carbon once it's up and running. Now that's kind of one of the catches is that first you have to get it up and running. It takes a lot of fuel to transport all that stuff up there. So it's not really totally free, but at least it is, certainly once it's running, it doesn't take much in the way of carbon-based power. That also is kind of ignoring maintenance as well. Ultimately, when things break, you're going to leave as much in place as you can, but at some point, you're probably going to be doing maintenance. Now, another interesting area is that this power can be redirected. So if you have solar satellites in a lower orbit, then they actually are blocked by the sun partially, but you could have, at different times, you could direct the power to one place or another. And so that's cited, maybe military use, maybe disaster relief, that kind of thing. Now, longer term, the assumption is that we won't have to lift all this stuff off of Earth. Longer term, we would probably want to mine the material off the moon, do the process, and there's plenty of elements on the moon to create solar cells, but it's obviously you have to set up the manufacturing operation. So it's kind of a bootstrapping problem. You're not going to start off with that. You're going to start off with things brought up from Earth, but eventually the hope would be you could lower costs fairly drastically by doing a lot more off of Earth. And there's no pollution on Earth either. But there's barriers. Why don't we see it yet? Well, the first thing is just cost. That's always been the problem. It's maybe 10 times, maybe 100 times more expensive than Earth-based power. The launch and the maintenance costs are the biggest killers right there, launch in particular. It's always going to be more expensive to take a solar cell and throw it up way up in the atmosphere as opposed to just installing it on the ground. You can't beat that. The space conditions are a lot more severe. In a high orbit in particular, the radiation's a lot higher. The panels may degrade maybe 8 times faster, is a figure commonly cited. And also, if you're going to have people involved in creating it, then they're exposed to more radiation at high orbits as well. So that's all kind of a problem. Even if you have robots doing it, robots depend on a lot of electronics, computing power to be effective. They are also quite vulnerable to that radiation. So that's a problem. The big issue also is scale. There is no such thing as a small solar-based system. And part of the problem is to transmit efficiently. Well, if you're using microwaves, the big problem there is that you're going to send it down to Earth. You can't have it be a very concentrated beam. You're going to fry everything in between. Birds, people, whatever. And it's kind of hard to do that, especially from my orbit. Even just the satellites in between are going to get affected. So that's an issue. The other thing is the microwave beams themselves, they spread out. So the typical solution is going to be assume maybe a kilometer-wide array out in space. You need a 10-kilometer receiving area to handle that. So it's got to be big. You just can't avoid that. Unless you're using laser power, and then you have the opposite problem. You've got this really concentrated beam, and it would destroy anything. If the beam drifted off, it's a weapon. It's not a practical power source. So there are some risks, collisions, space debris, all that kind of stuff. Interference with communications. You know, they're using microwaves. Microwaves are pretty much at the same frequency as a lot of the communications that go on. So there's a lot of use of those frequencies. Damage, of course, and they're vulnerable. You know, war, terrorism, those kinds of things. Technology issues. The atmosphere would absorb a lot of the power if you go to a higher frequency. You're restricted to maybe maximum 10 gigahertz in the frequencies you can use. There are a lot of losses in the overall process. When you transmit through the atmosphere, you can lose some power. You think about the whole process. You're starting off with light from the sun. It gets converted to direct current by the solar cells. It then gets converted back to an alternating current microwave, which is transmitted. It's received, it's converted to DC, then it's converted back to alternating current. There's a lot of steps in there. And anytime you have a conversion step, there's inefficiency. So that's part of the problem. So, yeah, there's some other things that go on. Heat dissipation turns out to be an issue. Solar cells are not 100% efficient. You have a lot of them up there. What happens to the energy that doesn't get transmitted? Well, it has to be dissipated as heat. And as Doug had mentioned, it's hard to dissipate heat in space. You can only radiate it away. So that gets to be a problem in its own right. Anyway, there's been a lot of arguments about this. So the proof will simply be, if people build it and it works, they'll have a last laugh. Elon Musk has taken a very strong opinion on this, as he has on most other things. He was interviewed in 2012 in one of these public relations things that like the one that Andrew's going to talk about. He said, space-based solar power is the stupidest thing ever. That was literally what he said. And then there was a follow-up. He had an interview with, I think it was Popular Account, and he actually said, stab that bloody thing in the heart. I mean, that's kind of his opinion. Now he has, of course, he has his own biases in that. I mean, he does, after all, have a company, Tesla, that makes solar panels and makes batteries, to ride you through the night when there's no solar power. So you might say, okay, he has a vested interest in not having this happen. On the other hand, of course, if you're putting up solar power satellites, that's a tremendous amount of business for his rocket company. So he has a little bit to balance there. Now, looking at it economically from his standpoint, he's seeing that there's a much bigger business in communication satellites than there is in the launch business. So he's probably still leaning toward, let's not do this space-based solar power. Just the fact that he's totally against it, makes you think twice anyway. There are other projects besides this Japanese one that I was talking about. We talked about NASA having a various number of these projects, and they go up and they go down, but nothing has really come of it. The Naval Research Lab did an orbital test. The X-37B, that space plane we talked about before, they actually took one up. They had a solar panel on the outside with the electronics to transmit the microwaves. They didn't transmit all the way back to Earth. They were just trying to measure how well it would hold up and how well it would convert the power to microwaves, and then how would it do over a long period of time. I mean, that thing was up there like a year and a half or so. So they found that out. There was some information that came out about it. They considered it a success. The Air Force has actually put up a $100 million contract for Northrop Grumman, who's going to do some satellite testing in 2024. Now they say they're looking for power to forward military bases. That one you have to kind of take with a grain of salt. I mean, it's hard to imagine them carrying, a 10 kilometer pile of metal, and putting that all around their military base out there in the middle of some forward base. So maybe they're looking at it with lasers, and maybe they're also getting kind of a dual use out of that. Caltech has a program that's going on for a while. They had a backer that also provided $100 million. This is just a private person, and they expect to actually launch something by 2023 to test this out. The UK may do a system. China's the big unknown. They have said they want to do this too, and they're saying they'll have small scale low Earth orbit tests in 2025, and they're hoping to have a megawatt size reactor up by 2030. We don't know, of course, how these will turn out, but anyway, there's definitely a lot of interest out there. It may or may not happen. Okay, quick thing on launches since the last meeting. We normally do a survey. We're kind of short on time here. Let's not even bother with that. Turns out that since the last meeting, which was January 8th, a little bit more than a month, there were 11 launches. And I'll just highlight a couple of those. One of them is on a Falcon 9, where they have a series called Transporter, where they pick up a lot of small satellites. And in this case, they took up 105. And this is really how SpaceX is competing against the smaller rocket vendors. So those guys are kind of afraid of these things. There will be another one of these because they are successful and they're a lot cheaper than the ones from, say, Rocket Lab or some of the others. Virgin Orbit put up one, or they put up 7 small satellites. They're the ones that dropped the rocket out of the plane, not to be confused with Virgin Galactic that does the space tours. And I can skip through the rest. OneWeb, this is the competition for Starlink, this for internet service from space. They're up to 428 satellites now. They kind of been, you don't get much press. Everybody hears about Starlink. Nobody hears much about their competition. They're up there. They're planning on having 648 satellites. They're up to 428 now. Now, Starlink has over 2,000, even after losing. They still have more than 2,000 that are up there. But they have to have more because they're in lower orbit. So they can't cover as much territory with each satellite. Yeah, I think I'll leave it at that. So at that point, discussion, questions, comments?
At this point, we had a brief discussion on the failure of the Astro rockets, and then a very lengthy discussion on the role of fission and fusion for future power sources. Unfortunately, the audio is way too garbled, so it's not reproduced here.
All right, so Andrea, we've already pretty much introduced her already. She covers technology and space in particular for the Houston Chronicle. I have some things on the slide here showing, you see her, she was, her story is on the front section of the paper today. Anyway, let's just turn it over.